Hey, Psych230 students. All right, now we're going to do the muddy points from chapter 7, which is the probability and sample means. So the first thing to understand is to, again, sort of think at the big picture. We've been learning about z-scores. Chapter 5 and 6 were z-scores for individuals, right? So basically, again, remember we started as a descriptive statistic. We could just locate where an individual is within a distribution of scores, so within a group of people. So same thing like on our test. We could look at where everybody's scores were in the class. And then if we calculated one of your, any student's z-score, it would tell us where they are. It would tell us whether they were above or below the mean for the group and how far above or below the mean in terms of a standard deviation. So that's essentially it as a descriptive statistic. And that was chapter 5. Then in chapter 6, we add on using the unit normal table, where we can now start looking at proportions, which really ultimately tell us probabilities. So we can look up what's the probability that somebody had a score above this point, below this point, between these 2 points, and so on. And so that's something that we learned how to do. Now, in chapter 7, we're going to basically do what we did in chapter 6, but instead of working with individual scores, we're going to work with sample means, meaning we're going to take a group of people and then calculate all their scores and then calculate the mean for that group. So that now we could look at that group mean and say, what's its z-score in a group of all the possible theoretical means we could get if we sampled the same sample from the population over and over and over and over again. And so that's what brings in this thing called the central limit theorem and so on. But to try to simplify this, I want you to just, again, focus on the fact that this is just like chapter 7. We're going to be doing the same things. Just like chapter 6. So in chapters 5 and 6, we had z-scores for individuals. Okay, so z-scores for individuals, if you wanted to calculate the z-score, you take that individual score, an x, subtract it from the mean, could be a population mean or a sample mean, and divide by the standard deviation. Okay, or if we wanted to solve for the actual individual score, that's our x, it equals the mean plus the z-score times the standard deviation. Now again, just remember the mu can be an m, and then this would be, instead of a population standard deviation, would be an s. So it's the same formula for populations and samples. So that's what we did in chapters 5 and 6, but now we're working with samples. And with these samples, we're going to end up with sample means. All right, and that's chapters 7 and 8 technically. Now, the formula, again, very simple, very similar, I should say. Instead of an individual score, we're now working with a sample mean. So we start with m. So we'll have how did our sample do? And then we're going to subtract that from the population mean to see how unusual a sample it is. And then we'll divide by standard deviation. But technically, this standard deviation is a standard deviation of sample means. It's this thing we're going to call standard error. We'll come back to that. And then again, if we want to solve for the sample mean, it is the mu again plus the z times this standard error. Again, that's standard deviation of the sample means. So you'll notice that these two formulas are pretty simple, or similar. Again, instead of an x, replace it with an m because that's what we're working with. Instead of an individual score, we're working with a sample mean. And then we have a standard deviation for those individual scores. We have a standard deviation for those sample means. Technically, this sigma could have an x in it. It'd be a sigma sub x. Okay? And that's essentially that. So then these two are very similar. Again, solve for x or solve for m. Use the standard deviation of x's or use the standard deviation of the sample means. Now, the only thing we need with this one is then the formula for that standard error. And that is the standard deviation of the population over the square root of the sample size. Okay? So that's basically the change, is we're going to have an extra step before we can even get to these two, either of these forms. You're going to use one of them probably, depending on which one you're trying to solve for, whether you're solving for a z or solving for a sample mean. But we're going to have to calculate a standard error first. Okay, so that's the first thing, is that it is basically very similar kind of steps that we did in chapter 6. just add one more. And then the other piece is this thing called the central limit theorem. And the central limit theorem is not something you have to understand at a conceptual level, and I'm not going to test you on the central limit theorem. You just need to know how to apply it. So here's where this is going to go. And I want to just take a question, like very similar to what we did in chapter 6. We would say something like, what's the probability of an individual having, let's say, an IQ score greater than 107? Okay. So we might ask that question, right? So it'd be something like probability of an X greater than 107, right? So that might be a question from chapter 6. From chapter 7, it would be, what's the probability of a sample mean greater than, and I'm just going to make it 103. So same kind of idea. So we can do that because what we can do is draw the distribution of all of the x's, is what we did in chapter 6, but now we can draw the distribution of all the sample means and then see where the sample mean of 103 would be, and then shade everything higher than that, and so on. So let's do this one. So let's focus on this. And what we're going to start with is, if we were asked this question, we would also be given information about IQ scores. We would be told that the mean is 100 and the standard deviation is 15. And we're going to take a sample size of 25. And this distribution is normal. If I don't say it's normal, that was one of the questions on the muddy points, just assume it's normal. And essentially IQ scores, a lot of the things that we use for this class will be normally distributed. So it just sort of saves us. Now, one of the things that we then do is we say, okay, if we're given this is the mean for individual scores. This is a population mean and a population standard deviation. So what I often do is I draw that distribution. This is not a step you have to do, but I do think it's a step that's really helpful, kind of grounds you in the problem. You locate the mean of 100. You can draw the standard deviation of 15. Okay, that is our distribution of individuals. So I label it with an X. Individuals will typically on this IQ test score right around 100, plus or minus about 15 points. So some people can be way up here where it's 130, 140, 150. Some people can be way down here where it's 70, 60, 50, and so on. But most people are right around 100, 110, 90, 95, 105, etc. There are a lot of people in here. Okay. So if we were answering it based on chapter 6, we would have just then located 107. It would be a little bit above the mean. We would shade above that, and we would know we're looking for a tail. We convert the 107 into a Z-score using this formula here, and then we look in the tail. But what we're talking about here is this question. What's the probability of getting a sample mean greater than 103 from this population? So what the central limit theorem says is, if we took sample sizes of 25, if I grabbed 25 people out of this population, remember this population here is individuals, there's thousands, hundreds of thousands, millions of them in there. So we just grab a random assortment of 25, pull it out of there, and we give them an IQ test, and we record their sample mean. And then we do that again, and then we do that again, thousands and thousands and hundreds of thousands of times. It's a theoretical thing. So we say, okay, well, what would those sample means all look like if we distribute them? Because, okay, let's say I take one sample mean out and ends up that that sample has an average IQ of 101. Great. Then we write that down. Then we take another sample and their average IQ is 99.3. And then we take another sample and their average IQ is 107. And their another sample and their average IQ is 83. And another 102, 107, 94, 99, 99.3, 101.6, etc. If we did that thousands of times, what would it look like if we drew the graph of the distribution of those sample means? That's what the central limit theorem tells us. It tells us three things. The first thing is that distribution of sample means will be normally distributed. Okay, so I draw my normal distribution. That's one of the three things. It tells us the shape. If we sample from a normal distribution, we will get a normal distributed sample means. Okay, so that's the first. Second thing it tells us, the mean of all these sample means will be the population mean. So the population mean is 100. That means all these sample means will be right around 100. They aren't going to be exactly 100. Some will be above, some will be below, but they should be near 100 because that's the mean for the population. And then the third thing it tells us is the standard deviation. But it's the standard deviation of these sample means. And again, that's our standard error. It has a standard deviation over the square root of sample size. So in our case, our standard deviation is 15. Our sample size is 25. So 15 over 5, or 3. So we should get sample means around 100 plus or minus about 3 on average. Sometimes it'll be higher, sometimes it'll be lower than 100. On average, it will differ from 100 by about 3 points. Sometimes more than 3 points, sometimes less than 3 points. So now this is the distribution of sample means, and that's then the one that we want to use to answer our question. What is the probability, if these are all the sample means I could get, just by chance, sampling 25 people from this population, how many of them, what proportion, or essentially this is not the probability, but what proportion of them will be means greater than 103? Okay, so I locate 103 here. 103 is going to be right about here. And I locate that because 103 is above 100, so I put it to the right, and then I shade every sample mean in this graph, I'm shading them red, that's above 103. Okay, because it's means greater than 103. All right, so now I know that's a tail. So now I know that I'm going to get my answer in the unit normal table in the tail column. Okay, so at that point, I can't look up the 103, that's a sample mean. But what I can do is look up a Z-score. And so what I want to do is I want to have a Z-score scale down here, and I know the mean is going to be 0 for a Z-score, and what I want to find is that Z-score right there. Okay, so I want to find that score. So how do I find that? Well, that's where we go up here, and we're going to use this formula. To calculate the Z-score, we take m minus mu over the standard error. So I'll write that over here. Okay, so in our case, it is 103 is the mean that we're interested in, minus the population mean of 100, divided by the standard error, which we calculated already, is 3. So this is 3 over 3, or a Z of 1.0. And I'm going to do it out to 2 decimals, because our unit normal table, the Z column, goes out to 2 decimals. So I know this is a Z of 1.00. So essentially what I need to know to get my answer is, what is the tail for a Z of 1.00? Now, right at the top of the second page on the right, there's my Z of 1.00. Go across to the tail column and I find 0.1587. And now I know my answer. And that is the probability that a sample mean, if I sampled 25 people from this population, there's a 15.87% chance that they will have a mean greater than 103. So not many, a minority of people, a minority of sample means would have that high of a sample mean. Most of the samples will have sample means less than that. It's going to be around 84% will be in this area here, somewhere below 103. So you'll see how that was very similar to what we did in chapter 6, in the sense that we've got a thing, we've got to locate the cutoff, we've got a shade to the right or to the left, depending on what the question is asking, determine if it's a body or a tail, convert that score to a Z-score so we can look that up in our unit normal table. The only thing that's different from chapter 6 is, one, we have to first start with the distribution of individuals and convert it using the central limit theorem to the distribution of sample means. The other thing that we have to add is the calculation of that standard error. Okay, but that's basically the main difference here. Now, the other thing we need to be able to do is be able to go from a proportion / percentage to the actual cutoff score. So again, we did these with chapter 6, where we would say, okay, what are the individual score cutoffs for the top 20%? What is the individual score cutoff? So at what point is the score that determines the top 20%? Or what are the score boundaries for the middle 80%? Okay, so what we want to be able to do the same thing, but now with sample means. So again, we're going to be using these formulas, basically following what we did last time, where again, except there's going to be this piece where we have to draw a second distribution, the distribution of sample means based on the central limit theorem. And then we also have to add in that step of calculating the standard error. So let's just do one of these just so we can kind of get an idea of, and one of the common ones, the ones that people tend to struggle with a little bit more, is the middle percentages one. So let's do one of those. So what if I want to know the SAT sample mean cutoffs for the middle, let's say, let's go with the middle, let's say the middle 99%, because again, this is a good example where we have to play around. Actually, we did that one with the chapter 6, so let's do the middle, we'll do 95% this time. So we want to know the SAT sample mean cutoffs. Oops. For the middle 95%. Okay. For a sample size of 25. Okay. Now, to answer this question, we need to know the mean and the standard deviation of SAT scores. Okay, the mean is 500. That would be given to you in the question. And the standard deviation is 100. So this is for a subtest on the SAT. All right, so what I would do first is I would draw my distribution of individuals. Oops. Decent. Okay, so I draw a normal distribution because, again, we would be told that this is a normal distribution. And again, if we aren't told it, we just assume it in this class. And then I know, so I draw my bell curve. And then I'm given to you in the question, the mean is 500 and the standard deviation is 100. Okay, so I can draw that. Again, I put an X here to indicate that this line right here is individual scores, an X. Now, so what I want, however, is the sample mean cutoffs. Okay, so that's important. This is not looking for the individual score cutoffs. It's looking for the sample means cutoffs. And then I need to look for the sample size. And I see the N of 25. Okay, so knowing that I have a sample size of 25 and that individuals are normally distributed, mean of 500, standard deviation of 100, I can then use the central limit theorem. Now again, you don't have to memorize what the central limit theorem says. All you have to do is be able to apply it to this and then say, okay, if I took samples of 25 people from this population over and over and over and over again, each sample of 25, they would each take the SAT, and then I could calculate their mean, the group's mean. So I'd take all 25 scores and calculate a mean. Each sample has a mean, but what I want to do is get a distribution of all the theoretically possible sample means I could get from this population. So that's going to be hundreds of thousands of sample means. According to the central limit theorem, the distribution of those sample means will be normally distributed. So I can draw a bell curve. Now I'm going to label it with an M because they're sample means now. So again, you get a lot more sample means here in the middle and fewer sample means out here on the ends. Why? Because they're going to have a certain tendency based on the population they come from, meaning that if I sample 25 people from this population, most of the time I'm going to be sample people who have scores around 500. And so the sample mean should probably be somewhere around 500. And that's in fact what it will be right around. So the first thing the central limit theorem tells me is the shape of this distribution of sample means. It will be normally distributed as long as we're sampling from a normal distribution. The other situation that we would need to know is if I wasn't sampling from a normal distribution, this will be as close to normal as we need it if the sample size is at least 30. Okay, so one of the things to know is if you don't have a normally distributed population you're sampling from, just make sure you have a sample size greater than 30 and you're okay. The distribution of sample means will be normally distributed. In this class, however, just so you know, every population we're going to sample from, any set of scores that we're working with, it will be normally distributed. So you don't have to worry about our sample size. Okay, because our sample size isn't big enough, but we know this will be normally distributed because this is. So that's the first part of the central limit theorem. Second thing you need to remember is it tells you the mean. The mean will equal the population mean. So we're told the population mean in the question. It's also in, this is the distribution of individuals. Means will have the same mean. Because, again, if I select 25 people from this population up here, their scores are going to be pretty close to 500. Plus or minus 100, but when we average out 25 scores, they're going to be pretty near 500. So that's where you get a higher curve here, near 500. Sure, we can get sample means that are very high or sample means that are very low, but those are just less likely to happen. So that's the second thing, tells us the middle. The third thing the central limit theorem predicts for us is the standard deviation of all these sample means. It's what we call standard error, and again, it's equal to the standard deviation of the population over the square root of the sample size. So in our case, the standard deviation is 100. Sample size is 25. So that gives me 100 over 5, or 20. Okay, so that's the standard deviation of our sample means. So this is 20. So we should expect any sample from 25 people will have a sample mean right around 500 plus or minus about 20 points most of the time. So you can get a big chunk of them here, somewhere between 480 and 520, because that's 20 points on either side, one standard deviation on either side. Okay? So, but our question says, what are the sample mean cutoffs for the middle 95% for a sample size of 25? So what I want to do is I want to shade the middle 95%. Okay, so I'm going to shade this part here. Okay, so what I've shaded there in the red is that middle 95%. So we've got 95% in there. So what we want to do is we want to find this score here and this score here. What are the sample mean cutoffs for this cutoff there and that cutoff there, the lower limit and the upper limit? Okay, to get there, what we need to do is figure out what proportion is shaded here so that then we can turn it into a Z-score. So what we're going to end up having down here is the Z-score scale. And what we want to find are these two Z-scores right here. Now what I know is when we convert things to Z-scores, the middle is always a 0. Mean for Z-scores is always 0, standard deviation is always 1. So what I first want to do is I'm going to convert this percentage into a Z-score cutoff. To do that, you have to figure out what I've shaded here so that we know which column we want to look this up in our unit normal table. Remember, we have our 3 proportion columns. We've got proportion in body, proportion in tail, and proportion between the mean and the Z. So what I have here is not a body, because the body would keep going, but this stops. So it would be like a body from here, but then that body would go all the way over here. So it's not a body. That kind of looks like a tail, but that's not shaded. So I don't know really what that is. That might be a little hard. What it kind of looks like for many people is this one. I'll put this on this side. Is what it looks like is 2 of these. There's one on the right and there's one on the left. And I'm going to shade the one on the right for you. Okay. So what I've shaded is a slice of exactly half of that 95%. Okay, so what I'll do, just to make sure I'm getting this right, I take the 95 and I divide it in half. And so we get 47.5%. So this is a slice equal to 47.5%. Now all I have to do is take that 47.5 divide by 100 to get a proportion. And that becomes 0.4750. Okay, so that's one way to figure out then what I need to look up. I need to look up in my unit normal table a slice of 0.4750. Another way to do it, and this is what some people will see, is that, again, they saw this little part as a tail, and so they can determine that this whole red part is 95%. What then that means is there's 5% outside of that. And because it's symmetrical, that means half of it's down here and half of it's up here. And they'd be able to figure out that this is a tail right here of 2.5%. Because there's 2.5% here, 2.5% there, that's 5%. Add that to the 95% and they're 100%. So that's how some people do it. Other people like to do this whole thing here and they just add the 2.5% here. So it would be a body of 97.5%, whatever works for you. But so what I tend to find is that a lot of people kind of see that it's two slices. So that's what I'm going to do. So I'm looking in my slice column. I'm looking for 0.4750. And on our third page, we're getting closer. 0.45, 0.46, 0.47, 0.4, yep, and there it is exactly. Now this is kind of rare, but we do have the exact proportion in our table. So I know that the Z-score cutoff for a slice of 0.4750 is 1.96. So at this point, then I say this is a 1.96. So now I have my upper boundary as a Z-score. Now, again, partly you want to remember, and this was one of the muddy points questions, is how do you know whether it's positive or negative, is any score above 0 is going to have to be a positive Z-score. But any score below 0 is going to have to be a negative Z-score. And so because this is symmetrical, I know this is the same Z-score of 1.96, but now it's going to be the negative 1.96. So technically right now what we found is the Z-score boundaries for the middle 95%. The Z-score boundaries are negative 1.96 and positive 1.96. But that's not what the question asks. The question asks, what are the SAT sample mean cutoffs? So we have to convert each of these Z-scores into the sample mean scores. So to do that, we use the formula that solves for sample mean. And that was what we had that I showed you on this previous page. Remember, we can solve for Z, but what we want right now is solve for is a sample mean. And so we use this formula. It's much like what we did when we solved for an X. Similar kind of setup. So the formula is mu plus Z times our standard error. So for this lower limit, I'll just call that LL. The sample mean will be our mu, which is again for this distribution, which is 500, also given to us in the question, plus the Z-score, negative 1.96. Because it's a negative, I'm just going to put it in the parentheses, times our standard error, which we calculated, and our standard error was 20. Okay, so now we can calculate that negative 1.96 times 20. So 1.96, make it a negative, times 20 equals 39.2, negative 39.2. So this ends up being 500 minus 39.2. And the difference is 460.8. Okay, so that is this one right here. So 460.8 is the lower limit. And then the upper limit is, again, the mu plus this Z-score here, the positive 1.96 times 20. And that's 500, in this case, plus 39.2, or 539.2. And now we have the Z-score cutoffs, or sorry, the sample mean cutoffs here for the middle 95%. And those are our answers. And when I say upper and lower, lower is always going to be the smaller number, upper is going to be the higher number. If it was Z-scores, lower is always the negative, upper is the positive. But in this case, it was asking for sample mean cutoffs. So that's really, the kind of the two things you need to be able to do is you need to be able to go from a sample mean to a proportion. And it's usually going to be phrased as probability. So what's the probability of having a sample mean greater than 103? And then the other way you'll have to go in the other direction is to go from a percentage to sample means. And so in this case, our answer was these two scores here. This score and that score. Those were our SAT sample mean cutoffs. So what does this tell you? It tells you that if I took a group of 25 people, gave them a subtest on the SAT, took their scores and averaged it, that group's sample mean should be between 460.8 and 539.2 about 95% of the time. There is there's a 5% chance basically that it is outside of this range. Okay, so that's main thing that we do in chapter 7 is just convert all of this to just now apply our calculation of this thing called standard error and apply the central limit theorem. That's how it really differs from chapter 6. What we're then going to be doing from here is going and applying this whole process, sort of both of these, but we're actually going to kind of be using this one almost specifically, the middle 95%, to determine what are the Z-score cutoffs for the extreme. And we're going to actually not need this last step. We're just going to need to calculate a Z-score for a sample mean. And we can then tell, is that sample mean part of that middle 95% or is it not? And this middle 95% we can almost think of as a typical or pretty average sample mean score without any kind of treatment effect. But if we gave a group of 25 people who take this SAT some kind of training program that we think is going to help improve their SAT score, we can then test, did it actually do that at a statistically significant level? And that's meaning that is the group going to ultimately score outside of this typical or average 95% group or number of sample means. So if we get a sample mean that ends up scoring above a 539.2, that might be a group that got this training, and the training might be the reason why they're scoring so high. That's kind of where we're heading. So I know a couple things that were in the the muddy points had to do with this is in terms of well, I guess let me read a couple of these. So so some people are just talking about how they the central limit theorem's kind of unclear. Again, all you really need to do, you don't have to memorize or really fully understand the central limit theorem. You just have to apply it. And so you just have to say, okay, if I go from a normal distribution, my distribution sample means is the same shape. And that distribution sample means will have the same mean that I'm giving in the question. And I can calculate the standard deviation of that sample mean. So if you end up having the mean and the standard deviation of all these sample means, you can then calculate z-scores and sample mean scores for whatever things you want as far as proportions and probabilities and all that kind of stuff. So it's really, you just have to focus on the application side of it. Somebody said to meet the conditions, you have to assume population is normally distributed. How would you know if it is or is not? The whole reason we're taking a sample essentially is because we don't know the population. So how do we determine this? Well, two things. One, again, as I said before, for our purposes in this class, we're always sampling from a population that's normally distributed. We assume that just that way we don't have to worry about that assumption. But in the real world, yes, that is a very good question. You know, we can't always, if we don't know the population, how do we know it's actually normally distributed? Ultimately, it doesn't matter as long as, remember, the second rule is that your sample size has to be at least 30. So as long as you have a sample size of at least 30, it doesn't matter what shape this one is. This one is going to be normally distributed, or as normally distributed as we need for our table to work and for our proportions to work out. So that's where just your sample size ends up mattering. And so we just make it easy in this class as we don't have to worry about that. But if you were a researcher, yeah, you just want to make sure you have a sizable enough sample, and 30 is a good minimum number. Let's see. Yeah, somebody also talked about it's like learning a new language, and especially like going from chapter 5 to chapter 6. It actually, there is a lot of overlap, and they're very similar, but then you do have this standard error thing, and that is a weird language thing. Just best thing to think about this is, one, it's in our purposes right now, it's often really useful to just think of it as the standard deviation of the sample means. That's why the M is in the subscript. Again, you can make the assumption that this one is technically a standard deviation of individual scores. So it would technically have an X in the subscript. However, by convention, we don't usually put the X. It's an assumption, which is like, if you're working with individual scores, that's a typical way to calculate standard deviation. So we just leave the X out. But when you do something besides an X, you need to list it. But it is sometimes helpful to just remember this is simply just the standard deviation of the sample means. So when we look at this graph, it is just telling us we know the mean of those sample means and we know the standard deviation of the sample means. Much like when we had individual scores, we know the mean of those individual scores and we know the standard deviation of those individual scores. That allows us to calculate z-scores. So that's one part. The other thing eventually is you want to be able to understand this, especially once we get to inferential statistics, is this has the name standard error. Standard, again, if you remember with standard deviation, is another word for average. Remember, a standard deviation is the average deviation from the mean. So think of this, when it says standard error, it is the average amount of sampling error. Because as it turns out, when we calculate a deviation from the mean for a sample mean, technically what you're calculating is sampling error. So let me show you one picture of that. So this graph here, or this picture here, kind of depicts that. Here we have a group of sample means. So this is based on what would a distribution of sample means look like. So we use the central limit theorem to determine this. Each of these boxes here is a sample mean. And you can see there's a bunch of sample means in the middle here, close to the population mean. That's what we'd expect. But you get some sample means that are a good bit away. Any difference between a sample mean and the population mean, we technically consider that sampling error. So if I said the average height of SCC students was 68 inches, and then I measured a group of SCC students to try to estimate the population height, and let's say my sample of SCC students from our class ends up being their average height is 65 inches. Okay, that might be like this one here. It's a couple inches shorter. That's sampling error. It's who I ended up sampling ended up not having a sample mean exactly the same as the population mean. And so as a result, any difference from this middle line here is considered sampling error. And what we're calculating here when we calculate this difference is a deviation. We just take the sample mean, subtract it from the population mean, and you get a deviation. So that's what a standard deviation is. The deviation in this case just happens to also measure sampling error. And so when we call it standard error, it is the average amount of expected sampling error. So some of the sample means have none because the sample mean is exactly equal to the population mean, but others have some positive sampling error, some negative, and again, we just sort of take that out by squaring the differences and all that. But ultimately, standard error just measures that average amount of expected sampling error. And we always, for the most part, really expect it. The vast majority of samples will have some sampling error. So that's the other way to think about it, and that's that language part that does get a little hard. Yeah, and then also somebody talked about how some of this, especially once you start getting to this part, the application inferential statistics, you don't really have to know this part. This is something we're absolutely covering straight up in Chapter 8, but it is just trying to prepare you for Chapter 8. And at this point, what we're really highlighting here is just simply that most research isn't done on an individual, so we've already kind of been preparing you for inferential statistics with research studies that kind of based on an individual. So like we gave one rat growth hormone and we wanted to see, is this going to be a heavy rat or not? But it's much more likely that research is going to actually take multiple rats. So they might take 25 newborn rats and give them growth hormone. And then we want to see, because again, that means you're going to more likely sample some rats that are likely to be heavy, some rats that are likely to be light, and some rats that are likely to be an average in terms of their weight. And so you're getting a more representative sample than just sampling one rat. And so that's a better research study. But we still want to know, is that sample really different than what we'd expect? And again, what the central limit theorem tells us is what a typical sample of rats would look like. So in this case, a typical sample of 25 rats would have sample means right around 400 plus or minus 4. So any of the samples in here are common typical not unusual at all samples. But the ones that are up here, in particular for our purposes, above 407.84 or below 392.16, the ones up here are unusually heavy samples. The ones down here are unusually lightweight samples. Something weird's going on there. It could just be sampling error. We just got a really heavy sample, or we just really got a really lightweight sample ultimately when they grew up. But the alternative explanation is that maybe what we gave them, this growth hormone, is what made them that weight, made them heavier or made them lighter. And so those are the two choices. And part of how we make the decision is that we say, okay, well, if I know that, let's say we get a sample of rats that weigh 408 or 409 or 410, that is out here beyond this cutoff, and it's noticeably different. And what we can determine is this cutoff can be based on a probability. In this case, what we decided was the middle typical 95%, and then everything out here is the extreme 5%, 2.5% on either side. So what we can then say is that if we ended up with a sample of 25 rats that weighs 408 grams, the likelihood of that is going to be less than 5%, because to be out in those extremes is only going to happen 5% of the time or less. So that's unusual. So we've got our two choices. It could be sampling error, or it could be the growth hormone. And because the sampling error option is a less than a 5% chance, those are low or poor odds, we're going to bet on this one. We can still lose. It can still be due to the sampling, but the probability of that is low enough that we're comfortable making a bet, and it is essentially an educated decision. So that might feel really weird, because then you think, well, okay, well then somebody publishes this, and does that then mean that growth hormone works? No, a growth hormone doesn't necessarily make these rats fat. It might, and actually probably the better way to interpret it is it probably does, because the likelihood that it doesn't is such a low probability, 5% chance, a 1 in 20 chance. But we need more research. And so you'll need to see another study that explores this. And if they find the same thing, give the rats growth hormone and they end up heavy, okay. And they have the same probability, 5% chance of that happening, okay. But now you've got two studies that had that same result happen. And then another study comes in, same thing, they end up heavier. Another study comes in, you get 5, 10 studies all showing the same result. Now we're starting to get more and more confident. The likelihood of all 20 of those, 10 of those, 5 of those studies coming out where rats weigh heavier is getting less and less likely to be by chance or sampling error. But contrast that with, if we did the first one, it ends up they're heavier, and then we do a second one and they don't end up heavier. They end up being, like an average of maybe 402. Okay, that's not unusual. At that point, we'd have to really question whether growth hormone is having much of an impact. And then another study says, nope, they're not any heavier. Or another one comes out, it might go back and forth for a while. And it just might be that there's a small effect, or it might be that there isn't one. That's how science works. And science is really a lot slower than probably many people want it to be. They want the answer right now. Science doesn't work that fast. Science is very exacting, and it takes time. Exacting in the sense of it doesn't care about time. It's just simply it's going to try to get it right, and it takes time, and it takes lots of research studies. So, but for now, again, you don't have to quite understand this, but then we'll eventually get to chapter 8, and then chapter 8 really starts to put it all together. And so that's where this is just kind of preparing you for that. And then hopefully by the time we get to chapter 8, things make a lot more sense. And now you can just follow the process. So chapter 8's the toughest. There's not going to be a muddy point, I don't think, for chapter 8, but I do want to point out that in, sorry, let's see, let me put this down here. Oh, it's not going to let me. Trying to get to this. Okay. Go here, there, now let me. All right. So in this, I want you to know that there is this specific thing. This is a video that is specific about hypothesis testing. And so instead of necessarily a muddiest point, it can be very useful. You're going to see these one of these every chapter now, because what you're learning now, every chapter, starting chapter 8, 9, 10, 11, 12, 13, 14, all of those are hypothesis tests, different types of statistics each chapter. And we're going to calculate a hypothesis test start to finish. And so what you'll see is a video that walks you through a hypothesis test start to finish. And it is inferential statistics. This is really kind of the focus of the class, because this is how we use statistics in research. So you'll see each of these, and then they kind of walk you through a bunch of calculations and how you do all of the steps of the hypothesis testing. So just be aware that those exist. And so that should hopefully help. All right. If you have any questions, as always, reach out to me. Thanks.